Today, we're going to take a trip down a mathematical rabbit hole into this really curious world of numbers that pop up in the most unexpected places. Seriously, it's like an Alice in Wonderland of mathematics. And our guide on this journey, it's a sequence called the Catalan numbers. So, you ready to dive in? Okay, so picture this. You're standing in the corner of, let's say, a checkerboard garden. You've got to get to the opposite corner, but here are the rules. You can only take steps to the right or steps going up. That's it. Seems simple enough, right? Let's say we're on a 5x5 grid. How many different paths could you possibly take? But, of course, there's a twist. There's this diagonal line that cuts right across our garden. Think of it as a forbidden path that you are not allowed to cross over. You can touch it, sure, but you can never, ever step above it. And just like that, our simple little walk has become a pretty fascinating puzzle. So, how many paths are left now? All right, so how in the world do we solve this? Well, first things first, let's just forget about that forbidden line for a minute and figure out how to count all the paths in general. We got to get our basic tools ready. The key tool we need here is a concept from math called a combination, which you'll usually hear as n choose m. And don't let the name scare you. It's a really simple idea. It's just a way of asking, if I have n total things, how many different ways can I pick m of them? For our path problem, this is the perfect tool. We can think of it like this. Out of all of our total steps, which ones are going to be our up steps? So think about it. On our 5x5 grid, no matter which path you take, you absolutely have to make 5 steps to the right and 5 steps up. Any other mix just won't land you at the destination. So what that means is that every single possible path is exactly 10 steps long. So the total number of paths is 10 choose 5. Right? Out of 10 total steps, we have to choose the 5 moments to step up. And when we run the numbers on that, it works out to 252. This is our starting point. 252 possible ways to walk across the grid if there were no forbidden line at all. Okay, now let's bring back that forbidden line. This is where the real story begins. Because now we have to separate all those 252 paths into 2 camps, the good paths that follow the rule and the bad paths that break it. And this shows the difference perfectly. Over on the left, that's a good path. See how it stays so neatly on or below that gray diagonal line? But on the right, that's a bad path. It starts off fine, but then, oops, it steps right into the forbidden zone above the line. Now, to put it a little more formally, for a path to be legal, or what we're calling good, your y-coordinate can never be greater than your x-coordinate. In other words, you just can't have taken more up steps than right steps at any point in your journey. Now, trying to count all the good paths directly is, well, it's really tricky. They can hug the line, they can dip way below it. There are just so many variations. But here's a classic problem-solving move. What if, instead of counting what we want, we count what we don't want? What if we could just count the bad paths? And that question leads us to the most elegant, most beautiful part of this entire solution. It's this clever little trick that honestly feels like stepping through the looking glass. We're going to transform our bad paths into something else entirely. So here's how the trick works. It's a really simple 2-step process. You take any bad path and you find the exact moment, the very first step that it takes to cross above that diagonal line. Then, for every single step after that point, you just swap it. Every right becomes an up, and every up becomes a right. Let's just watch it happen. So here's our bad path on the left. It crosses the line, and right from that point on, we swap all the remaining steps. Now look at the path on the right. It's not a path to 5-5 anymore, is it? By swapping the tail end of the journey, we've created a totally new path that ends at a completely different spot, 4-6. Okay, but what's really wild is that this works for any bad path. Here's a completely different one that crosses the line much earlier. We apply the exact same trick, swap everything after that first violation, and wait a minute, look where it ends up. The exact same destination, 4-6. And you know what? That is not a coincidence. And this is the crucial insight, the whole key to the puzzle. This trick establishes a perfect one-to-one relationship. Every single bad path that was supposed to go to 5-5 can be transformed into a unique path that goes to 4-6. And it works in reverse too. This means that counting the number of bad paths to 5-5 is the exact same problem as counting the total number of paths to 4-6. And with that one magical insight, we are finally ready for the grand finale. Let's put all these pieces together and actually calculate the answer to our puzzle. The logic now is just beautifully simple. The number of good paths we've been searching for this whole time is just the total number of paths we started with minus the number of bad paths that we now know exactly how to count. So here's how the math breaks down. We already know the total paths to 5, 5 is 10 choose 5. And our swapping trick showed us that the number of bad paths is the same as the number of paths to 4, 6. Well, a path to 4, 6 needs 4 right steps and 6 up steps. That's still 10 total steps. So we can count the bad paths by calculating 10 choose 4. The total, 252, minus the number of bad paths, which is 210, leaves us with 42. That's it. There are exactly 42 legal ways to walk from one corner of a 5x5 grid to the other without ever stepping above the diagonal. And this number, 42, isn't just some random one-off answer. It's actually the 5th entry in this amazing sequence, the Catalan numbers. For a 1x1 grid, it's 1. For a 2x2, it's 2. For 3x3, it's 5. Then comes 14, then our answer 42, then 132, and it just keeps going, following this beautiful, predictable pattern. So you might be thinking, okay, cool, grid walking puzzle, but why should I care? Well, because this isn't just about grids. This sequence is one of those magic threads that weaves its way through countless areas of math and science. I mean, the Catalan numbers also count the number of ways you can arrange parentheses in a formula, or the number of ways you can build a binary search tree in computer science. They even show up in patterns in the folding of RNA molecules in biology. The fact that they appear in so many places that seem totally unrelated tells us there's some kind of fundamental structure they're all secretly sharing. You know, this quote really captures the elegance of the method we just walked through. We took this rule that applied to the entire path, a complicated global condition, and we found a clever way to solve it by focusing on just one specific moment, the very first time the rule was broken. That's just a really powerful way of thinking. This whole reflection principle we used, it's like a beautiful piece of mathematical jujitsu. And sure, it solved our specific puzzle, but it leaves us with a much bigger, much more exciting thought. It just makes you wonder, what other simple, elegant tricks like this are out there, just waiting to reveal all the hidden connections that tie the world of numbers together?